All right, in this video and the next video, I'm going to talk about indeterminate forms and L'Hopital's rule. I'll talk about what that means exactly. So um, earlier when we looked at limits at the beginning of the year, we saw that sometimes we're trying to find a limit. We get to this indeterminate form such as infinity over infinity or 0 over 0. Um, in some cases, we were able to work around these using some algebraic methods, and sometimes we aren't. So this lesson, we're going to learn about a technique we can use, a method known as L'Hopital's rule, that will allow us to evaluate some of these limits that result in indeterminate forms that we can't deal with in the way that we dealt with them earlier in the year. So things like this, sine 4x, so the limit as x goes to 0 of sine 4x over 2x. That's something we can't really do with what we had before. All right, so this is L'Hopital's rule. I'm not going to go through the proof of it. I want you to just this is the main thing here, is that if I have f and g are functions that are differentiable on this open interval AB containing c, except possibly at c itself. So maybe they're not differentiable at c, but on the rest of the open interval AB. And g prime of x, the first derivative, is not 0 for all x in AB except possibly at c itself. If all that's true, then this is true. The limit as x goes to c of f of x over g of x is equal to the limit as x goes to c of f prime of x over g prime of x, provided that the limit on the right exists or is infinite, and the limit on the left results in an indeterminate form. So if I've given this, and this results in an indeterminate form, then I can say, well, that's equal to this one over here, the limit as x goes to c of f prime of x over g prime of x. Let's talk a little bit about indeterminate forms. The ones that we saw earlier in the year were, things like infinity over infinity, 0 over 0. There are others. 0 times infinity is 1. Infinity times infinity is 1. Sorry, that's wrong. Not infinity times infinity. That's just infinity. No problem there. Some other ones, I don't know. These are kind of weird ones. 1 to infinity, 0 to the... Basically what it means to say that it's an indeterminate form is that there's nothing we can tell from this about what the limit actually is. And like we don't really get any information from any of these, so it's indeterminate. It may turn out that there's just nothing to find out, but we're going to look at cases where we can find something out even when we get one of these weird things like this. Note that some things aren't, not indeterminate forms. Include things like, 0 over infinity. That's okay. That's just 0, right? That equals 0. You're going to 0 on the top. You're going to 0 on the... Basically, that means you're going to 0. Infinity over 0. Another one. That's just infinity. Those are fine, but these are the indeterminate forms. So let's look at a couple cases. How does L'Hopital work? Well, look at this one. Limit as x goes to infinity of 2x plus 1 over 4x squared plus x. Notice what happens if we try direct substitution. We get 2 times infinity plus 1 over 4 times infinity squared plus infinity. So that's going to give us 2 times infinity plus 1 is just infinity. Similarly, 4 times infinity squared plus infinity is infinity. So this is an indeterminate form. Okay? So this is where we want to use L'Hopital. Remember, we can only use L'Hopital when we get an indeterminate form. So we'll say this is equal to the limit as x goes to infinity of the derivative of 2x plus 1, which is 2, over the derivative of 4x squared plus x, 8x plus 1. Okay, now I can use direct substitution, because what happens when I use it direct substitution? Now I get 2 over 8 times infinity plus 1, which is just 2 over infinity, which is 0. And I'm done. So all I had to do was take the derivative of the numerator and the derivative of the denominator, and then I was able to use direct substitution from there. Another case down here, limit as x goes to 1 of ln x squared over x squared minus 1. And if I try direct substitution, I'll just do that right down here. I get ln 1 squared, right, over 1 squared minus 1, which is going to be 0 over 0. So I get 0 over 0 if I try direct substitution. So I'm going to try lhopital now. All right, so what do I get? I get 1 over x squared times 2x, remember chain rule, over 2x. At this point, I can just say, I could cancel these out. I get limit as x goes to 1 of 1 over x squared. And that's pretty straight, 1. And so then I get direct, now I can use direct substitution, right? Because I get 1 over 1, which is just 1. No problem. So in both of these cases, you see, like I start out, I get some sort of indeterminate form. I can't deal with it with what I'm given, but I can, using L'Hopital's rule, I basically take everything down one level. I take the derivative, differentiate both the numerator and the denominator, and I'll end up with something that's easier to deal with. All right, why don't you try this one on your own? You want to just pause the video here, try this one, and then I'll come back and I'll go through it. Okay, so limit of x as x goes to 0 of sine 4x over 2x. If I try direct substitution, which I'll just do right here, I get sine of 0 over 2 times 0. So I just get 0 over 0. So there's an indeterminate form. So that tells me I can use L'Hopital. Remember, you can't use it if it's not an indeterminate form. Don't just go trying this all the time. All right, so this should be equal to the limit as x goes to 0 of 4 cosine 4x, that's the derivative of sine 4x, over 2. What happens now? Now I can do direct substitution, right? Because I get 4 times cosine 0 over 2, which is just 4 over 2. Cosine 0 is just 1. 4 over 2 is 2. Pretty straightforward. Let's look at, here's a question. Yeah, so what are we doing when we use L'Hopital's rule? This is a worthwhile question. And to put it another way, I'd say, why is this important? I mean, you might get to this and you think, well, how often are we going to really need to evaluate limits of this form, f of x over g of x, where we can't do it by direct substitution? Here's an example, and this is one of the important ways that we use L'Hopital as we go on. Suppose that f of x equals e of x, and g of x is x squared. You can see pretty easily that both of these go towards infinity as x goes to infinity, right? This goes to e to the infinity, which is really big. This goes to g of x goes to infinity squared, also really big. But it is a worthwhile question, and in some cases it's an important question. Which of the two functions goes to infinity, quote unquote, faster, right? Which one's getting there for? Which one's going to win the race to infinity? And this turns out to be important. L'Hopital's rule gives us a way of answering this question. So consider this limit. The limit, so I'm taking f of x is e of x over g of x, which is x squared. The limit as x goes to infinity of e to the x over x squared. Okay, well, we already saw that direct substitution ends up with infinity over infinity. But what happens if I use L'Hopital's rule? Get e to the x over 2x. Well, at this point, if I try direct substitution again, I'm just going to get e to the infinity over 2 times infinity. So I'm going to have infinity over infinity. If I try direct substitution, get infinity over infinity. So what can we, you know what though? Now I've just got two new functions. I've got the limit as x goes to something of one function over another function. And L'Hopital's rule says that that's going to be, if that results in an indeterminate form, it's equal to the limit as x goes to that same thing of the derivative of the one function over the derivative of the second function. I'm just going to do L'Hopital again. I get e to the x, and then change, over 2. Now, I know, okay, limit as x goes to infinity, e to the x. So I can take direct substitution, e to the infinity over 2, or infinity over 2, which is just infinity. Why did I do that? Well, that tells me something. What is it tells me? I remember I was saying, well, we could use this to figure out which of the two functions goes to infinity faster. That e to the infinity is going to be going much faster than 2. E to the infinity is going to beat out, sorry, x squared. Because if x squared was going to infinity faster, then this limit would have ended up being 0. Another way to put it. All right, so that's all I'm going to do for this. Oh no, sorry, one other thing I want to point out, and I've sort of emphasized this as I've gone along, but I want to show you. L'Hopital's rule does not apply to limits that do not result in indeterminate forms. So take an example like this. See what I mean? Look at this. Limit as x goes to 1 of 2x squared over x plus 1. Well, if I tried direct substitution, I'm using blue for direct substitution. So then I've got 2 times 1 squared over 1 plus 1. Oh, and I just get 2 over 2, which is 1. So there we go. That's the limit of 2x squared over x plus 1. But what happens if I try L'Hopital? Well, I would say, okay, the limit as x goes to 1. I would take the derivative of the numerator, which would be 4x, and the derivative of the denominator, which would be 1. So I get limit as x goes to 1 of 4x. Oh, well, the limit is, now I can use direct substitution, and I get 4 times 1, or 4. I get a different answer. This one is wrong, right? I mean, we know the limit, right? We just did, if you can do it by direct substitution, that's your answer. But if you don't have an indeterminate form, if that limit does not give you an indeterminate form, do not use L'Hopital. Do not use L'Hopital. Check first to make sure that the limit gives you an indeterminate form. Otherwise, you're going to end up, you're going to do stuff, and you can see you get a completely different answer. Okay. In the next video, I'll go through a couple examples that get a little bit more, little trickier. All right.